Okay, so today we will do a hands-on session for some parallel programming. It depends on how much we can progress, but I won't do anything new in terms of like algorithm. I will just run the same old direct n-body code that we have been using to compare against checking the answer. So that's the simplest code I have, and so I'm going to start a new line of code that's called like a parallel .cxx, and I'm running like a parallel. I named my first code parallel1.c. So this is sort of not a continuation of step 1 through 8. So I'm naming it differently. So now I'm at step 1 again for the parallel code. It's a direct summation code that uses the same kind of variables. It's x, y, u, q, and all it does is it calculates the n-body interaction directly. So here it's looping over I and j, and it's calculating this dx, dy, r, and then it's the same thing. It's just the thing that you had at the end of your code that said check answer in steps 1 through 8. So this has been existing in your code for steps 1 through 8. I'm just using just this part now, because one of the features of this thing is it's very short, and also it's very parallel. So I can test all kinds of parallel models like OpenMP. I can test the SIMD, SSE or AVX, and I can also test CUDA, for example. So let's try to program this part in all these different parallel languages and see how much it accelerates. So the first test is this one. Just so you don't have to go through the pain of coding this, I will just upload this to Google Docs, and you can just download and then run this code. The code itself is not so complicated, so you can maybe just run it if you want. But I'll just upload this file to the Google Drive so that you can see it from the lecture web page. It's called parallel1.c. And the only difference between the previous codes is that it has the pragma OMP parallel 4. I didn't mention what this thing was. So private j is because I'm defining j somewhere up here, and I'm using it here. But if I don't write here private j, what's going to happen is it's going to share this variable j among all the parallel threads. And I mentioned that data sharing was an issue. What happens is, so example, if you had 2 threads, thread number 0 is going to start looping over j, and it's going to assign some value to j. And if thread number 1 is also looping over j, it's writing a different number to j every time it increments, and it results in some strange behavior. So if you write private j, that means all the threads don't share this variable j. Also, if you define something like double dx, double dy, double r inside the function, inside of the pragma OMP parallel region, then by default it's private if you define it inside. The problem with j is it's defined somewhere else. It's defined externally, so you have to declare that it's private. For example, some values I don't want to declare private. X and y and q are defined somewhere else. But I don't define them private because first of all, they're just being read. No one's writing to them. Also, ui I'm also writing to, but I'm not defining as private. Why is that? Because when OpenMP separates this loop I from 0 to n, this is going to get split into different groups. So what this pragma OMP parallel 4 does, it changes this for loop into a parallel loop, and so one of the threads is going to process from 0 to 10, and then the next thread is going to process from 11 to 20, and so on. So I will get split into different groups. But then UI, I don't want to make it private because I want these different threads to write to the same U. So this u I want to share, except since I is split into different groups, they will never write to the same u location. They will not write to the same, for example, u0 to u11, only the first thread will write. And u12 to u20, maybe only the second thread will write. So these variables, u, q, x, y, I am not specifying as private. They're shared. Okay, so that's sort of the rule for OpenMP. And now that we know what we are running, let's do some tests. So how you compile this is slightly different from the previous one. You need to write here -OpenMP. So you need a compiler. If you're using GCC, I think it needs to be at least newer than 4.3. So if someone types this and they get an error, please raise your, no. If someone types like this and gets an error, please raise your hand, because most people should be able to run with this option. Is everyone able to compile? Well, first of all, does everyone have parallel1.c in their computer? Yes? Okay. If this gives an error, I can help you make it compile. So see if this works. Is everyone? Because I want everyone to be able to actually do the comparison. Yes. It's okay? No, you get some. No such file. Do you have parallel 1?
No.
You need yeah, can you download the parallel1.c from?
Oh, okay, I download.
Yeah, you can download from
This.
Yeah, this one. Or you can just create a new file and copy this. You have it here.
Yeah.
Okay, so can you compile here? No. This is in this machine.
Yeah.
Okay, you need to send it. Yeah, can you send it with like some software?
Okay. I don't know how to send it.
Which machine is this one?
This?
The one you were doing GCC. This was a different machine?
I don't know. Actually, I don't familiar with this.
Well, so you can just copy and paste this. I think that's easier. Yeah, and just on the machine that you were running. Yeah, this one. Just create a new file with some editor, and then copy and paste it. So just create the parallel1.c. Where's the dot? Is this it? Oh yeah. Parallel1.c. Okay, and now you just need to no? How did you copy? How do you paste? No? You need to can you copy again? Oh, okay. So now you have this code, so you can run GCC. No? What happened? Does this say 1 or L?
Oh.
Okay, now it's complaining about the code itself, so that's good. There's some symbol defined in this code that is confusing the compiler.
Oh.
This one. I need to delete this. Okay. Okay, so now if you run this with time, then it returns the time. So this is the timing. So you can well, I'll tell you what to do next, but you can change the number of threads. Is able to run? Okay.
I already run it.
You run, okay. Ah, okay. I just need to know if you're okay. So, I hope everyone is able to run, because you won't be able to enjoy today's hands-on if you don't run, because it's not about new code. It's just about running the same code on different number of threads and different environments. So, okay, so now I'm going to do time. So if you just do a.out, you won't see anything. But if you write time and then a.out, this actually gives you back, and what you need to view is this thing that says real. This is the time it took to run your code. And so this means it's using 2 cores, because the user thing is the sum of all the cores. And so it's running at half this, it's using half the time per the total. So that means it's 2 cores. Yes?
Problem. He said the supporting option.
Ah, okay. So I think your GCC is old. Is it this machine, or is it where are you now?
I'm on the terminator.
Okay.
I use the Xcode compiler.
Clang. Okay, can you log into some other terminal? Yeah, you. Because this GCC doesn't support OpenMP, I think.
Yeah. I think in the machine we gave you the account, you can run that. I just checked that. If you remove logging, you got the percent owner. Yeah. So you need to upload the file there. But I just checked. You can run.
Yeah. Also, so if your machine doesn't support this, you need to log into the the account that was created for you, and if you don't know how to copy the file there, the easiest thing to do is open this file and manually copy the contents. Just do like a Control C here, and then go to your new machine and then open a empty file and then copy it in. Then you'll have the file there. You don't need to know how to transfer the files. If you know how to use things like SCP or rsync, then just use those to transfer between the 2 machines. Okay, so I'll move on. Now I'm going to do an experiment. So the environment value OMP num threads controls the execution of OpenMP. So if you set, well, this is if you're using bash. If you're using, like C shell, you need to use setenv. But I think most of you are using bash. So run export OMP num threads equals 1. And now look, I'm doing the same thing, time a.out. But now the real says it's taking 1 second instead of 0.5 seconds. That's because originally I had set OMP num threads to 2, but now I've set it to 1. And then you see that controlling, I think you can also control the number of threads by just saying OMP num threads. This, I think, overrides, or no, it doesn't. Is it this way? Yeah, so if you write like this, you can manually override what you set in the environment by saying time OMP num threads. It says in the environment value 1, but please override it to 2 and then run this. So what happens, I don't know how many cores I have on this machine, but maybe you see what happens if I say 4. it's not exactly 0.25. It's taking a little bit longer. And so when you write parallel code, it doesn't get completely 4 times or however many times faster. There's always some place where it slows down. And this is called the parallel efficiency. So if the parallel efficiency was 100%, then this should say 0.25 or roughly, or 0.26 maybe, if it's exactly half of this. But it's not exactly half. There's some inefficiency that starts to appear for larger and larger number of threads. I don't know how many cores I have on this machine, but let's try 8 and see what happens. Okay, now it's slowed down. Oh, so this is a good example of where the parallel efficiency doesn't help you. Maybe I should first check the number of cores on this machine before I yeah, so this machine has only 4 physical cores, so that's why doing 8 doesn't help me at all. Okay, it has only 4 cores, so up to 4 it speeds up. So I'm doing this experiment for different number of threads, and when I do 8, it no longer speeds up because the machine only has 4 cores. If I move to a machine that has more cores, then I will probably see more speed up. You can also, if you're on any Linux-based machine, if you do top and then press 1, then it will show you how many CPUs you have. So you can issue this command to see how many cores you have. Okay, so, or actually threads, running threads, it will show. Okay, so now let's do something else to the code. Okay, so this is step 1. Well, maybe they're all going to be direct summation, so maybe I'll just write here OpenMP because this is an OpenMP example. Okay, now I'm going to copy this to step 2 and see if I can change this into like a SIMD vectorized code. Okay, so now let's see. I'm going to grab an example from my other codes. So in the meantime, everyone can experiment with different numbers of cores, and if it's not speeding up at all, then you can try to see what's wrong.
对，